Good evening, everybody. I test 1, 2, 3. I test 1, 2, 3. Still loud and clear. I test 1, 2, 3. I test 1, 2, 3. So, students, this is loud and clear. You can put on the chat. Now it's perfect, no, Akila? Now you can hear loud and clearly. We'll start in another 5 minutes time. Right. Good evening, everybody. This helpline session is actually just to help you all start doing questions at home. Because normally what happens is when the workload increases, generally what happens is you all feel a bit bored or lazy to start the work. So during the week, mid session, just as a help for you all to get started studying, just to get you all in a group, small method or process. We'll be doing this helpline session. We'll continue to improve this helpline session, and there won't be a problem. Continuously, we will work this out. So it will be very helpful for you. So this is called a helpline session. We'll be discussing some important questions as well. All of you all know the homework questions that we have given you all. Also along the line, we will add in some more additional papers, school papers, and make this a bit more colorful as we go along. But for now, we'll just get this going in this particular manner. Right. So if you take your tudes page number 2, MCQ 6. Page number 2, MCQ 6. Right. So the question is completely based on hydrostatic pressure. So what are they saying here? Now the theory, remember, a stationary vessel with a liquid of density rho falls freely under gravity. Now we learned that as you fall freely under gravity, what happens? No liquid will be inside. No liquid will be inside the beaker. Just as when you fall from a lift, your feet won't be touching the ground. Will feel free fall. What will happen is, you will, there will be no fluid inside the beaker. Since there is no fluid inside the beaker, outside pressure and inside the fluid, the pressure will be the same. So MCQ number 6, MCQ number 6, here, the stationary vessel falling freely under gravity. Falling freely under gravity. So what you can do is, you can take a small cylindrical, these we have done, MCQ directly you should remember. These are the ones we have forgotten. Here you have atmospheric pressure into area. Here you have pressure into area. And don't forget, the weight of the fluid is also there. So if the beaker is falling down under gravity, downward forces are PATM times A. mg is acting downward. P times A. Here you go, mg. mg cancel off. PA equals PATM A. From here, AA cancel off. P equals PATM. So wherever inside, you will get the atmospheric pressure. So in this case, in this question, they are given you atmospheric pressure is A. So anywhere at a depth h, the pressure will also equal to what? A. Pressure will equal to A. So 6 MCQ answer is answer number 2. 6 MCQ answer is answer number 2. Right. MCQ 7. MCQ 7. MCQ 7. A rectangular wooden block floats on water, immersing 2/3 of the volume inside water. So you have 2/3 of the volume inside water, 1/3 will be above it. 2/3 of the volume inside water, 1/3 of the volume above it. 1/3 of the volume above it. When it is put in another liquid, it floats, immersing half of volume in water, in the liquid. Different liquid. Now half above, half below. Half above, half below. Now how will you mark the forces? So you can mark the forces clearly. Weight of the object is acting downward. Here upthrust in water is there. Got it? Here weight of the object is acting downward. Upthrust from the liquid is there. So we can take the density of water here as rho W and the density of liquid here as rho L. Rho L. They are asking the relative density of the liquid, right? So here we can say sum of forces in the upward direction balances sum of forces in the downward direction. Upward forces is upthrust in water balances the weight. Now be a bit careful. Huh? Be a bit careful. Upthrust is submerged volume 2/3 V. Density of water into G, that is equal to mg. We can say equation number 1. We can say equation number 1. Now in liquid, we can say sum of forces in the upward direction balances sum of forces in the downward direction. Downward direction. Upthrust in liquid balances weight. Upthrust in liquid here, V over 2, density of liquid into G, that is equal to what? mg. Same weight, same object, same weight. Now what? Now you can simplify the relationship. How will you simplify the relationship? Look at this carefully. Equation 1 and equation 2 both are equal. Equation 1, equation 2 both are equal. Now what? Simplify. 2/3 V rho WG, V over 2 rho LG. Simplify the relationship carefully. GG cancel off, VV cancel off. Now what? Density of liquid over density of water. So rho L2 comes on top, 4 over 3. This is the relative density of the liquid. Huh? This is the relative density of the liquid. So that is going to be 4 over 3, answer number 4. Answer number 4. You want to write a small sentence there? That is small sentence. Same object is floating. The same object is floating. The same object is floating in liquid. The same object is floating in liquid as well as in water. Therefore, in both instances, the upthrust will be equal. In both instances, the upthrust will be equal. In both instances, the upthrust will be equal. Okay. Right. So remember the same object floating on 2 different liquids or 3 different liquids, whatever happens, because downward forces mg is the same, the upthrust will also be what? Same. So direct connection, remember that. Right. Start it over here. Once you are writing, can write. MCQ number 9. MCQ number 9. Right. MCQ number 9. Here, a canoe means like a boat. A canoe with a mass 30 kilogram and volume 1 cubic meter floats on water. The boat is floating on water. Density of water is 1000 kilogram per meter cube. Maximum number of men with mass 60 kg each that can be borne by the boat without it sinking. Now, if this is the water level, the boat without sinking means on the verge of sinking. On the verge of sinking. Without sinking means on the verge of sinking. Now, what are they telling you here? Weight of the boat separately is 30 kg. That's 300 newtons, so 30 G. Here, 60 kilogram people are there. N number of people are there. 60 into, let's say, mark it as X. 60 times X into G. Now, upthrust is X due to what? That's all. Sum of forces in the upward direction balances sum of forces in the downward direction. Sum of forces in the upward direction, upthrust in water, 30 G plus 60 X G. So upthrust is submerged volume. They are telling you the boat volume is 1 cubic meter. That means the boat structural volume. 1 cubic meter density of water into G, 30 G plus 60 X G. G cancel off. 1000 here, 30, 60X. Right. Now, what are they asking you here? So here, if you simplify it, 970 because 33 is about 60x. 0, 0 cancel off. Now what? Dominahari. I don't can say answer 97 divided by 60 can't do. No? Right, so we divide it 1. 16.1. You can't have 16.1 men. You can't cut half of the man and put the fellow in. So approximate the number of men. But 60. That's it. You can't cut 0.1 man and put no that. Can't take place. You ignore that. So on the verge, that means if I put 17 men, the boat will sink. So maximum I can put 60. You can't put half a man, 0.1 man, 2.2 man. No, maximum 60. Anything more than that, the whole boat will sink. Right? Anything more than that, the whole boat will sink. Right. So there are answer number 3. Then comes the next one. MCQ 11. Very interesting. There is a nice vessel like this. A liquid with density rho is filled up to a height h in a cone-shaped flask. The liquid is filled up to a height h in a cone-shaped flask. The height is here. Now, concentrate. Huh? If the area of the bottom of the flask is A, and the volume of the liquid inside is V. So total volume inside is V. The force on the circular surface. The force acting on the circular surface. Now, focus. Huh? Now, if you look at this carefully, pressure will act perpendicular to the surface. So, what I'll do is, I'll just take the liquid out. There you go. Conical shape. The liquid will be like this. With a small gap, I will draw the vessel. Small gap. Huh? With a small gap, I'll draw the vessel. Now, look at this carefully. If you take the liquid only, weight of the liquid is acting down. Here from the bottom, reaction is acting up. Now remember, pressure forces will start acting in that direction. So liquid will push the vessel in that direction, perpendicular to the surface due to pressure. Liquid will push the vessel in that direction, perpendicular to the surface. I'll just draw these two. The liquid pressure is pushing it in that direction. Now, if you look at this carefully, I just took two symmetrical points. If you look at this carefully, here, if this is alpha, F cos alpha will cancel off. Horizontal components will cancel off. F cos alpha, this side F cos alpha. I'm just taking a point and doing it. F cos alpha will cancel. So cos alphas cancel off, but sin alphas remain. F sin alpha will remain. Now every action has an equal and opposite reaction. Reaction will act on two separate objects. Now F cos alpha here means equal opposite F cos alpha there. I'll just mark that. Concentrate. Okay. Here F cos alpha. Here F cos alpha means equal opposite. The lines of action should be the same. Okay, lines of action should be the same. If I slightly redraw this, slightly redraw that. F is here, alpha is here, F cos alpha, F sin alpha, lines of action should be same, so be careful. Here you have F cos alpha. Now don't forget F sin alpha will act down. F sin alpha will act down. So on this liquid, you can see horizontal components will cancel off. This is a very small thing. I just showed it. So liquid is pushing the wall in that direction. Wall is pushing the liquid in the opposite direction. Liquid is pushing the wall perpendicularly. Wall will push the liquid in the opposite direction. So cos components cancel off. Only the vertical components will remain, depending on where you take the angle. Now just look at this carefully. Now just the liquid. Don't really worry about the horizontal component. Now you have, here you go. Vertically you have forces acting downward. Plus you have the weight. Then you have what? The reaction created here. Reaction created there. So what are they asking you? A liquid of density rho is filled up to height h in a cone-shaped flask. If the area of the bottom of the flask is A and the liquid volume is V, the force acting on the cone shape, that means circular shape. So simple, no? Sum of forces in the upward direction balances sum of forces downward. Upward direction reaction there, mg plus. This reaction is due to the pressure acting at the bottom, force acting at the bottom, pressure acting at the bottom. Pressure acting at the bottom is what? H rho g times area will give you force. Mg plus F. A H rho g, volume into density V rho g plus F. F is equal to A H rho g minus V rho g. There you go. That is the force on the circular section. That is the force on the circular section. Now what they are asking is force acting on the cone or force acting on the liquid. Right? Understand it. Force acting on the circular section. I mark the forces on the liquid, but equal opposite force will act on the circular cone. So here this is on the liquid. Every action has equal opposite reaction. Every action has equal opposite reaction. So here, therefore, force on circular shape in vessel. Vertically downward force, there's a vertically upward force. The value is A H rho g minus E rho g. There you go. I hope you understood this. So if you take the liquid column here, you have weight acting at the bottom, normal reaction. Pressure forces, everywhere these pressure forces will act. If you take a dam construction, if you take the hydraulic, you have Victoria Dam, you have Pulgolla Dam, you have different types of notches, gears, etc. The pressure acting on that, if the liquid column is stable, it's always going to be perpendicular to the surface. So perpendicular to the surface means horizontal components cancel off, vertical components will remain. Vertical components remaining means here vertical components, horizontal components cancel off, vertical can't cancel. Every action has equal opposite reaction, F sine, F sine, F sine, F sine. So here there is a resultant force downward, horizontal components cancel off. So on the liquid column, we found the vertical force acting downward from the circular shape. Every action has equal opposite reaction. So on the circular shape, it's in the upward direction, which means your correct answer is answer number 2. Answer number 2. That is more sentence there. The pressure will create a force. The pressure will create a force on the circular section perpendicular to the surface. On the circular section perpendicular to the surface. We can show that the horizontal components will cancel off. We can show that the horizontal components will cancel off. But the vertical components will remain. But the vertical components will remain. But the vertical components will remain. We balance the forces on the liquid column. We balance the forces on the liquid column. We balance the forces on the liquid column. There will be an equal opposite force acting on the circular section of the vessel. There will be an equal opposite force acting on the circular section of the vessel. There will be an equal opposite force acting on the circular section of the vessel. Right. MCQ number 12. MCQ number 12. MCQ number 12. Right. Have a look. As shown in the figure, one end of a uniform rod is hinged to the wall of a vessel and the other end is immersed in water. So one end hinged to the wall, the other end is immersed in water like this. Right. The rod can freely rotate above the hinge in the equilibrium condition. That means clockwise moments equals anti-clockwise. Half of the rod is immersed in water. Half of the rod is immersed in water. So let's say here you go. Here. Half of the rod is immersed in water, right? So here pivot section is A. Pivot section is A, right? Relative density of the material of the rod. Think carefully. Very important. Half of the rod is immersed in half here, half here. Center of gravity is acting exactly at the center. There you go. Center of gravity is exactly acting at the center. Now it's very familiar. You all know this. Whatever you know, you put into a picture. Simple. You just put into a picture without being afraid. Then you know upthrust will act. Now where will upthrust act? Upthrust will act at the center of buoyancy. Where is center of buoyancy? Center of gravity of the submerged section. So upthrust in water is there. They're saying water, no? Yeah, water. Now, center of gravity of the submerged section means this length is L over 2. The other length is also L over 2. Right. Now, that's the hinge point. If this is theta, don't forget, we'll make it easier. I'll take an easy angle. You take the angle with the vertical. Angle with the vertical means easier, no? Right here, theta, let's say. Here, theta means here, theta. Here, theta means here also theta. Right. Now look at this carefully. Line of action. When you're taking moments, here L, here theta. This is L sine theta. L sine theta. Right. Line of action draw. Here you go, line of action. Here L, this is half of L, so 1.5 L. L plus half, 1.5 L. L plus is L over 2. So that is also L over 2. I'll erase additional angles drawn just to make it easier for you all. Here you go. This part is L over 2. Right. L over 2, 1.5 L over 2, take component. 1.5 is 3 over L sine theta. There you go. The equilibrium condition, clockwise moments equal anti-clockwise moments. Clockwise moments about this particular section. Here you go. Be careful. mg times L sine theta. Anti-clockwise moment, upthrust in water multiplied by 3L over 2 sine theta. 3L over 2 sine theta. Simplify this carefully. L sine theta cancel off. L cancel off. There you go. Observe this carefully. Now, be a bit patient. You can see the cross-sectional area here is A. What is the mass? Cross-sectional area into total length. Total length is 2L. Density of object will give you mass. Mass into G is weight. They want you to find the relative density of the rod material. So this whole volume is cross-sectional area into total length. Cross-sectional area into total length is A times 2L. You can see here to here L, here to here L. Make it easier. Density of object into G. Upthrust is submerged volume. Submerged volume is A times L. Only half is submerged. No? Density of water into G. 3 over 2 is here. Don't forget. Now what? Simplify this further. Simplify this further. Here you go. Area cancel out. This is the area. Area of rod. Cross section area of rod. Cross sectional area of rod. Right. G cancel off. Right. L cancel off. Correct. Density of object over density of water. Bring the 2 down. 3 over 4. 3 over 4 you will get. Correct answer is answer number 4. Correct answer is answer number 4. Right? Correct answer is answer number 4. So you can see it's not difficult. Whatever additional symbols we have used, it gets cancelled. So remember, sometimes they won't give you these symbols in the exam. Why? Whatever additional symbols you are using, automatically will what cancel off. Now, what are the additional symbols? I have put L here. L is not there in the answer. I have put A here. A is not there in the answer. Why aren't they giving those? G is also not there. Why aren't they giving those? Because those will cancel off. But to solve the problem, you need those. Okay, no? To solve the problem, you will need it. Right. Okay. MCQ 40. MCQ 40. MCQ 40. Right. A solid hemispherical object, hemisphere, half of a sphere, with a weight of W as shown in the figure, is hanged inside a liquid with density rho. If the tension in the string is T and the area of the hemisphere of the flat surface is A, magnitude of the resultant force acting on the curved surface of the hemisphere of the liquid is curved surface here as well. So important thing is, do not panic. Curve section, tension is acting at a depth S. So we know. So curve section forces, you can easily find. Weight of the object is W. Weight of the object is W. Now don't go and mark pressure. By resultant pressure force, pressure forces will start acting on the curve surface. These are very interesting, important questions. So without marking the upthrust, you can mark the pressure force because we know resultant upward pressure force is upthrust. Here. resultant upward pressure force is upthrust. Right. So let's say the hydrostatic pressure there is H rho G times A. Hydrostatic pressure force. Hydrostatic pressure. Weight is acting down. Now look. Now I'll analyze it separately. Yeah. So Minahari, curve section. Pressure forces is applied this. No? I took both sides. The objective is always whenever you see a curve section, don't panic. That means that you have to think a bit more in terms of basic theory. Do not panic. Now here you can see there will be a force acting here, there will be a force acting here. These are because of hydrostatic pressure forces. So why aren't I marking the upthrust? Resultant upward pressure force is what? Upthrust. So if I mark the pressure forces, don't mark the upthrust. That's the rule. No? That's the rule we learn. Here you have alpha. I'm taking two symmetrical positions. Here you have alpha. F cos alpha, F cos alpha. Tell me what will happen. F cos alpha will, what will happen? F cos alpha will what? Cancel off. F cos alpha cancel off. So what's there? F sin alpha is there. If you are a math student, if you add all the F sin alpha, that will give you the resultant downward pressure force on the curve surface. Horizontal forces cancel off. So F sin alpha, all the F sin alpha, then F sin beta, F sin eta, beta, all the F sines you can add on. Adding means vertically downward. Right. Adding means vertically downward. Now what? On here I'll mark. Here I'll mark the resultant force from the curve section. Resultant force from the curve section. F curved. Resultant force from the curve section is downward. So now what? Easy, no? Sum of forces acting upward, balances sum of forces acting downward. T plus A H rho G W plus force on curve section. So force on curve section you can find. Force on curve section is equal to T plus AH rho G minus W. Okay. T plus AH rho G minus W. Answer is answer 4. Now little by little you are getting right. Curve means horizontal components will cancel off, vertical components will remain. These things are now a bit by bit getting familiar. I mean, it's easier. That's how it goes. Right? There you go. MCQ 15. MCQ 15. Density of water is 1000 kilogram per meter cube. Density of ice is 900. So ice is less dense than water. If something is less dense than water, that means it will float in water, right? The minimum volume of ice cube that should have for a bird of mass 2 kg to stand on the ice cube, while ice cube. So secretly they are telling you it's a cube. Huh? Ice cube is here. Here, let's say bird is there. There you go. Bird is there. Bird is there. The fellow is not sinking. Huh? Both sides you have water. The fellow is not sinking. Right. Let's mark the forces. If you mark the forces, 2 kg bird, 20 G. You might say, what about the normal reaction? Now, be smart. You have finished everything and come to mechanics. Bird is pushing the ice down, ice is pushing the bird up, reaction will cancel off. Because we are taking the bird and the ice block. MCQ, no, the level is a bit big. Since you are in a higher level, quickly you should be able to what? Cancel off the reaction. Bird and ice reaction will cancel off. Weight of ice is there. Weight of ice is there. And don't forget, upthrust on ice is also there. It's a cube. I hope you remember cube means what? No, cube means every side same. L cube. Volume is L cube. What are they asking you? Minimum volume. They want the volume. Don't worry much. Sum of forces in the upward direction, balancer. Sum of forces in the downward direction. Upward direction is upthrust acting on ice. Downward direction is weight of the bird. Weight of the bird. Weight of the bird 2g plus weight of the ice. Upthrust on ice. Submerged volume, density of water into g. 2g. Mass of ice, volume of ice, density of ice into g. There you go. All the g's cancel off. All the g's cancel off. G cancel off. G rho W is 1000. G 900. Simplify the relationship. Simplify the relationship. V 100, 900 means 100 V 2. V is equal to 2 over 100. 2 over 100 is 1 over 50 cubic meter. There you go. 1 over 50 cubic meter, answer number 2. 1 over 50 cubic meter, answer number 2. Answer number 2. Right. MCQ 18. MCQ 18. MCQ 18. As shown in the figure, a metal ball with volume 4 10 to the power minus 4 cubic meter, volume of the ball is given, is submerged in interface where there is mercury and water. As half of it is immersed in mercury, the other half will be in water. So what's happening? You have mercury at the bottom, you have water at the top, water at the top, mercury at the bottom. Half of the object is immersed in mercury, half in water. So 1 half in mercury, 1 half in water. 1 half in mercury, 1 half in water, right? Volume is given now. So what is there? Don't forget the weight of the object is there. Upthrust from water is there. Upthrust from mercury is there. That's all. Submerged in water means there is upthrust from water. If it's submerged in mercury means there is upthrust in mercury. Simple. That's it. So now what? Sum of forces in the upward direction balances sum of forces in the downward direction. Upthrust from water, upthrust from mercury balances the weight. There you go, mg. Now, what are they telling you? Upthrust is submerged volume in water, half of this. Half of 4, no, 2, 10 to the power minus 4. Density of water, 1000 into G. Upthrust in mercury, half the volume, 2, 10 to the power minus 4. Density of mercury is given, 13,600 G. They are asking you weight of the object, 4 10 to the power minus 4, density of object into G. Now what? Simplify this, all the G's cancel off. To simplify this, 0.2 is there. If you simplify this, 1, 2, 3, 4, 12, 7, 2, 2.72 is there. Here, 4 10 to the power minus 4, density of object. Simplify this, 2.92 is there. 10 to the power positive 4 divided by 4. Density of the object. When you are dividing, quickly divide. Simplify this. 0.73. 0.73. Sorry, Oh, they're asking the weight directly. So you don't have to do all of this. Directly they're asking weight, not the density. So mg, g cancel off. 2.92 kilogram will come. 2.92 kilogram will come. Answer is answer number 3. 2.92 kilogram will come. Answer is answer number 3. Right. MCQ 90. MCQ 90. 3 vessels ABC with the same mass. Same mass, important. 3 vessels ABC with the same mass. That means vessel mass is same. Right? There you go. Same areas at the bottom. Areas at the bottom same. Same areas at the bottom. Fill with water to the same level. Fill with water to the same level. Right. If you are filling it to the same level, what can you say? Looking at this itself, this volume is larger than that volume, larger than this volume. V1 is larger than V2, larger than V3. So weight of water here is much more larger. Obvious. It's a very obvious thing. Right. What are they asking you? FA, FW, FC, and the weight of the vessels of with water are WA, WB, WC. So technically, WA is larger than WB is larger than WC. This is without a question. Huh? No question at all. Weight of the water plus beaker added together, this will have a bigger weight. This will have the next weight, that will have the smaller weight. Right. What are they asking you here? Forces on the bottom. Now, forces on the bottom occur because of what? Hydrostatic pressure. Hydrostatic pressure is independent of the volume. Hydrostatic pressure at the bottom here, everywhere is what? H rho G. Here hydrostatic pressure, H rho G. Here hydrostatic pressure, H rho G. How do I find the forces? Multiply by area. If I multiply by area, now don't forget PATM is also there. Just the gauge pressure. If I just take the gauge pressure, hydrostatic pressure at A, B, C, all are what? All are same means answer is answer number 5. Answer is answer number 5. Answer is answer number 5. Okay. So you can see now, little by little, when you start doing questions, you get confident. And once you get confident, you go into a small flow. Once you go to a small flow, what happens? You just keep on doing it. Remember, every time when you're studying, the first 20 minutes, if you can hang on, if you are bored or tired, the first 20 minutes, do something challenging. What happens then is what? Then you go to a small flow. Once you go to a flow, you just can keep going. You just can keep going. Right? Question 21. Question 21. Right. A vessel containing a liquid with density ρ1 is placed on a weighing scale. Now, weighing scale problem. We are done. Theory. And a piece of metal of mass m and density ρ2 is held on a string immersed in a liquid. I told you. Somebody who can remember, you can type it in the chat. Here, when I immerse an object here, will the weight of this object act on the scale? Will the weight of this object act on the scale? Yes or no? Answer in the chat. Will the weight of the object act on the scale? Yes or no? Answer. Will the weight of that object act on the scale? No. Then tell me what will act on the scale? What will act on the scale? Answer. Samir was right. Samir Ziad, Answer is no. Weight is not acting on the object, on the scale. Then what is acting on the scale? What is acting on the scale? Or what are the forces acting on the scale? Tell me, Vilu. What are the forces acting on the scale? So here, if you look at it, here the weight of the object is mg, tension is T. Tell me, what is the other force acting here? What is the other force acting here? What is the other force acting on the small mass? What is the, now Muhammad Abdul was correct. What is the other force acting on the mass? Now here there will be a upthrust. Here there will be upthrust. Here there will be upthrust. Tell me. Every action has an equal opposite reaction. If there is upthrust, then what do you have? Downthrust. If there is upthrust, there will be a down. And also weight of the beaker is there, weight of water and beaker is there. Weight of water and beaker take as m1g. Here beaker is pushing the scale down, scale is pushing the beaker up. There you go. Right. Now what are they asking you? A vessel containing liquid density ρ1, this liquid is ρ1. So you can mark the forces. You can mark the forces on the object. Sum of forces upward balances sum of forces downwards on the object. To mark the forces on the object, T plus upthrust balances weight mg. T plus upthrust is volume. What's the volume? Mass over density. Mass over density is volume. Mass over density is volume. Mass divided by density of the object is volume. Density of the liquid into G. Look. Tension is equal to mg minus mg ρ1 divided by ρ2. Mg common 1 minus ρ1 divided by ρ2. Right. Superb. The tension is found. Right. Now what's happening? They're asking you cut the rope. What will be the reading in the scale? What will be the reading in the scale? Now look. First we'll go here now. Still. Sum of forces in the upward direction balances sum of forces downwards on the beaker. So on the beaker we have reaction R1, weight of the water and beaker M1G. I'll just keep it as M1G. Down thrust is there. Down thrust is same value here. Simple M ρ2. I'll mark it as U first. And then we'll do the substitution. M1G plus M ρ1 ρ2 G. There you go. React. This is the reading in the scale. Reading in the scale. Okay. Right. Reading in the scale. Now what are they asking? If I cut the rope, now if this rope is cut, if the rope is cut, what will happen? The mass will come down and slowly touch the beaker. Mass will slowly come down and touch the beaker here like this. Thing will become slack. Okay now? Thing will become slack. Slack means no what? Slack means no tension. Right. Weight of the object is mg. Don't forget upthrust is still acting. If there is upthrust, no space, I'll mark here. Downthrust is acting. Weight of the beaker with water is also there. Now be careful. Now don't be in a hurry. If you look at this carefully, I'll draw it with the additional gap. Actually, there is a gap. Purposely, I'm drawing it. Purposely, I'm keeping this gap. These two are touching. Okay. Mass will push the beaker down. Beaker will push the mass up. Okay. These two are touching. Then the scale is there. I'll keep a gap there. Or beaker is pushing the scale down. Scale is pushing the beaker. Now look at this carefully. Now sum of forces in the upward direction balances sum of forces in the downward direction. Sum of forces in the upward direction on the object. You might say, sir, it's so long. No, I'll teach you the theory and then the shortcut. Upward forces are 2. Upward forces are 2. Upthrust balances weight. R2 is equal to upthrust. Upthrust we found here. M over rho 2, rho 1 G equal mg. R2 is equal to mg, take it out, 1 minus rho 1 over rho 2, right? Now we'll take the beaker. Now take the beaker. Sum of forces in the upward direction balances sum of forces in the downward direction on the beaker. On the beaker you have R3. On the beaker you have R2. On the beaker you have down thrust and you of course have the weight. On earth is R2. R2 is here. mg minus, let's open bracket, mg rho 1 rho 2. What is u? U is same here. mg rho 1 over rho 2 plus m1g. These two will cancel off. These two will cancel off. Look carefully. R3 is equal to mg plus m1g. Now I'll name this double star. I'll name this reading here star. Double star and star. Now what has happened? Big looks like a big problem. No, it's not a big problem. Now they're asking you, what is the now if the string is cut, the reading of the scale will be. What is the reading of the scale? So once you cut the string, here you go, the reading of the scale. If you look at this carefully, a vessel containing a liquid of density rho 1 is placed on a weighing scale as shown in the figure. Metal of mass m, density rho 2 is held by a string is immersed in liquid without touching the side. Now, if the string is cut, the reading of the scale will, what will happen? So R3 is the reading. This is R1 initial reading. What has happened to the reading? Reading has changed. Let's see by how much. Let's see by how much. Change in the reading. Change in the reading. This minus that. R3 minus R1. R3 minus R1. Look carefully. mg plus m1g minus R1. Minus m1g. Minus minus means minus m rho 1 rho 2g. M1g cancel off. Once you cancel M1g off, this is what you get. mg minus mg rho 1 over rho 2. Take mg out. 1 minus rho 1 over rho 2. Right. Answer is there. Answer number 2. But my God, this is an MCQ. Now, how to do this quickly? Simple. Look. I want to ask you a simple question. Didn't you get the same answer somewhere else? Yes. Where did you get the same answer? Tension. You got the same answer somewhere else. Yeah, tension. Right. Now, before cutting the string, the tension was this value. After cutting the string, the tension becomes 0. So what has happened? The reading has changed. By how much has the tension changed? Initially tension mg1 minus rho1 minus rho2. Now tension is 0. Tension has disappeared. Remember, whatever disappears actually adds somewhere else. Actually, where has it added? It has added to the scale read. So tension disappears means the disappearing value adds somewhere else. So the disappearing value means the tension. Initially tension T, finally tension 0. Initially tension T, final tension 0. Tension has disappeared. Disappearing value adds somewhere else. And that's the adding to the scale. So disappearing value means tension disappears. So the simple idea is if tension disappears, that's to the read. That's to the reaction. If what you call reaction disappears, it will add to a reading. It will add to the reading bottom. So tension disappears, it has added to the reading. Correct answer number 2. So this is the working. One by one logical working. But the shortcut is what? Tension was there. Now tension is not there. Right. So the difference in tension adds to what? The difference in the reading at the bottom. Is it clear? Understood? Look at the workings again. Is it clear? You can ask questions if you want. Understood? Perfect. What has disappeared? Tension has disappeared. Disappearing tension will add to the weight. Is it clear? You can answer. In the chat, you can type. Okay. Disappearing tension. Tension initially is there. Now tension is not there. So disappearing tension adds to the reading of the scale. Okay, no? Clear? Right. So here you go. The disappearing tension disappears. So the MCQ, what I'll do is I'll always find the tension. I know tension disappears. R is the reaction. Beaker is touching the scale. Scale is pushing the beaker up. Okay. This is the reaction because of touching. Here it's touching. These two are touching. I'm drawing a big gap there just to mark the reaction. Is actually this picture is like this. This picture is like this. If I mark like this, then I can't mark the forces. No? So with the gap I have marked. Okay. Right. So disappearing tension will add the reading below. Okay, no? Right. Have a look. Maybe we'll do a few more questions and then finish it off. Question 24. Question 24. Question 24. A polythene bag contains 10 to the power minus 4 cubic meters of water with no air bubbles inside. Lowered into the bath, so there's a polythene bag, thin polythene bag. Outside was a water. Inside was a water. Outside was a water, inside was a water. So volume containing is 10 to the power minus 4 cubic meters. So here tension is there. Don't forget weight of water is there. And on this volume there is upthrust force action. Sum of forces in the upward direction balances sum of forces in the downward direction. Tension plus upthrust balances weight. Upthrust is submerged volume, density of water into G. Weight of water inside is minus 4 10 to the power 3 G. You can see these two cancel off. Tension will become what? Tension will become 0. Tension will become 0. Okay. MCQ 25. MCQ 25. So here you have a J tube. Olden days, these tubes were there, but they are in use. There you go, J tube. Liquid is here. Liquid is there. The difference in pressure they are given you as H. Here the pressure is going to be P1. Here the pressure is going to be P2. What are they asking you? What is P1 equal to? Same level, pressures are same, right? Pressure at A equals pressure at B. Pressure at A is P1. Pressure at B is P2 plus H rho G. So P1 is equal to P2 plus H rho G. Equation. Answer number 2. Answer number 2. Answer number 2. We saw 2 more questions. We saw 2 more questions. Question number 28. Now looks familiar. Huh? Looks familiar. Here you go the beaker. Here you go the beaker. They are saying AB is a thin uniform rod made from material rho, freely hinged at A to the wall, containing liquid of density rho, sigma. When equilibrium, 1/5 of the rod is projected outside. 1/5 projected outside means 4/5 is underwater. 1/5 above means 4/5 below. What is the ratio? Sigma over rho. So uniform rod pivoted here. Weight is exactly acting at the center. Exactly at the center means L. Exactly at the center means L over 2. There you go, L over 2. Upthrust will act at the center of buoyancy. Center of buoyancy is center of gravity of the submerged section. Upthrust in the liquid. That is going to be 2L over 5, exactly half of the submerged length. So, just like the earlier question like this, we'll take the area as A. Right. Clockwise movement, balancers, anti-clockwise movement. So you can see, once you know this, quickly you can find it. Clockwise movements, balancers, anti-clockwise movements. Now be a bit careful, okay? Be a bit careful. Here 1/5 outside, 4/5 underneath. 4/5 means exactly half of that only upthrust is acting, center of buoyancy. This length is L, this is 2L. So best is I'll mark the length separately. I'll mark the length separately. Mark the length separately. Right. So here you can mark it 2L over 5. Right. So with the vertical, let's say theta, here also theta, here also theta. Perpendicular distance here is 2L over 5 sin theta. 2L over 5 sin theta, right? Upthrust is acting, center of gravity of the submerged section. OL over 5 exactly half is 4L 2L over 5. Here this line. Here L over 2 sin theta. clockwise moment mg L over 2 sin theta. Anti-clockwise moment upthrust into 2L over 5 sin theta. Now just like the earlier case, simplified sin theta, L cancel off. What is the weight? Cross-sectional area into total length. Density of object into G. Upthrust is submerged volume. OLO 5 times A. Density of liquid into G. 2 over 5. Simplify this very carefully. Simplify this very carefully now. Simplify this very carefully. You can easily say A cancel off. L cancel off. G cancel off. Whatever. That's about it. No? Rho will come. Rho. Is rho. Rho will come. You mark in blue. Rho will come. Rho is sorry. Density of the object is rho. Density of the liquid is sigma. Right. Density of the object is rho. Density of liquid is sigma. Right. Okay. Rho over sigma. Rho divided by sigma is, look at it carefully, 25 at the bottom. 4 times 2, 8. 8 times 2, 16. 16 divided by 25, answer number 1. 16 divided by 25, answer number 1. 16 divided by 25, answer number 1. So simple. MCQ 30, good number to stop. MCQ 30. Vessel contains oil and mercury. Metal floats at the interface with one half immersed in mercury, other half immersed in oil. Nice. One half immersed in mercury, other half immersed in oil. Upthrust in oil is there, upthrust in mercury is there. That balances the weight. They are asking the density of the metal is. Sum of forces in the upward direction balances sum of forces in the downward direction. Sum of forces in the upward direction, upthrust in oil, upthrust in mercury, balances the weight mg. Now what? Upthrust in oil, let's say V and V, density of oil into G. Here V, density of mercury into G. Total volume is 2V, density of object into G. Now what? Simple, no? Cancel this off. G, V, cancel. Rho naught plus rho mercury, 2 times density of object. There you go. Now what? Now work basically. Density of the object is density of object plus density of mercury divided by 2. That means what? Density of oil 800 plus 13,600 divided by 2. So here you have your value. 14,200, 14,400 divided by 2. 7,200 kilogram per meter cube. 7,200 kilogram per meter cube. Answer is answer number 4. Answer is answer number 4. Right? So even this, remember, pressure is independent of area. Very important rule. Hydrostatic pressure is independent of the area. Some of you have asked about this. From there you can balance and get your answer. If you want, you can write it there. Hydrostatic pressure independent of what? Cross-sectional area. Okay, no? Right. So I hope the session was useful. Okay? So we'll build on this very slowly. As we gather on, we'll gather momentum. maybe we'll start with one day a week and then improve to 2 days, and then you see where it goes from there. Okay. Hope you'll get something from this. Whatever you learn from this, make sure you apply every day. You can see the time we started at 8:15, and so 1 hour we nice to solve the problem. So this start with 1 hour. Then gradually you can increase what your time. Remember, there is time for you to improve. Improvement you can happen every day. Make sure you improve every day. That's the most important. To improve every day, make sure you start doing. Once you start doing, inch by inch, mark by mark, you will improve. And once you improve, that is for you. You have achieved that. Good luck. See you all next.